Okay guys, so far you have completed or worked through 3 of the 4 sections of assignment 7.1 in Biomechanics unit. This video relates to the 4th and final section of assignment 1, and I'm just going to start by giving you the context in some sporting examples. So before this you've studied linear motion, positional change, an object changing its position in a certain direction, taking a certain time, and therefore moving in a certain speed or velocity. We've recognised what scalars and vectors are, and we've looked at how objects can accelerate or decelerate based on their rate of change of velocity. So this final section really builds again on this and talks about motion and how we either create or change or resist motion. So a bit of a bizarre example, but let's just start by looking at these crash test dummies here. So I'm sure you may have all seen images or videos of what happens with crash test dummies when they are basically driven into a solid resistance or a solid object. In the same way this happens to you in a car if somebody stops abruptly, or if you're on the train or the bus and it stops abruptly. Even though the vehicle has put its brakes on, the motion that you possess continues and you shoot forward, and hence we wear seatbelts in a car. So we've got this motion which wishes to or desires to continue in its normal path or the route that it's been it's been travelling in until something stops it. And the reason we wear a seatbelt is because we want this belt to be a resistant force that stops that motion so that we don't, of course, go into the front windshield. Here's another bizarre but, again, relatable example. We've got 2 vehicles that have broken down, a big lorry and a small car, and we've got a recovery vehicle. Now, if I just move this out of the way in a minute, if this recovery vehicle was trying to pull or tow this big lorry, it would have to rev up a lot, generate a lot of force, i.e. put your foot down, to be able to start this lorry moving from its stationary broken down position. Once it gets going, it's a bit easier, but that initial movement and trying to get that lorry to go from stationary to motion is pretty tough. Compare that to the recovery vehicle towing this little tiny car here. So from stationary to get this car to move, the recovery vehicle wouldn't have to put foot down quite as much, generate as much force to pull it. And I'm hoping you can recognise a pretty obvious difference between these 2 vehicles. Similarly, we've got a sporting example. So for this athletics athlete to push this shot and project it into the air, that's quite a tough job compared to this table tennis player having to project this table tennis ball into the air when they throw it up for the service. And again, hopefully you'll recognise there's a pretty obvious difference in the 2 objects that we're talking about and why it's harder for this athlete than it is for this athlete. Now you'll see in the title here I'm talking about something called inertia and overcoming inertia to change motion. So from this shot put being stationary and tucked into this athlete's neck, we've got to apply a force to push it and ultimately send this shot put off in the direction of its flight path. To serve, this table tennis player has the ball flat on their palm. They have to apply a force to the ball to send it vertically up in the air so that they can execute the skill of the service. Now, this shot put and this table tennis ball, when they are in the stationary positions, tucked in the neck or on the flat of the hand, have a reluctance to move. They don't want to move, essentially. And that's called inertia. It's not a reluctance to move, it's a reluctance to change its state of motion. So still on this player's hand, this ball doesn't want to change its motion. It wants to stay stationary. or this shot put wants to stay stationary in the neck. And what's got to happen to change its motion is we've got to apply a force. Now, logically, this table tennis ball has a small mass. It's tiny and light. It's light. It's not very dense. Therefore, the force we need to apply to push it into the air is very small. But we apply a force which is bigger than this table tennis ball's inertial value. This shot put has a different inertial value. It's a much denser object. It's got a much greater mass, 8 kilograms, I think. In order to change this putt's motion, this athlete, as you can see, has to apply a much greater force to overcome the inertia of the inertial resistance of this shot put. This of 7 kilograms, this shot putter has got to apply a much greater force to make it change its motion. Different example, we've got two opposing forces. These two opposing forces, if this scrum was stationary, would be balanced. Greens are pushing, applying the same amount of force as blue. At that point, there's a reluctance for a change in motion. What's got to happen to change motion of this combination of these two teams is one team's got to apply a bigger force. That means there's unbalanced forces. That basically means one force is stronger in one direction and overcomes this resistance or reluctance to change and pushes one team backwards. So some of the language there I've used is relevant to the topic. So we've got two sort of topics in one in this section. I've talked mainly about inertia in that little introduction, but you may, I know that you will use momentum in some of your daily language and be familiar with it. So this is the specification. You can pause the video and have a little look at it, but I'm going to go through this essentially bit by bit. First of all then, let's look at inertia specifically. So inertia is the tendency of a body to resist its change or resist a change in its state of motion. And that means whether it's still or stationary or moving, it's reluctant to change its state of motion. If an object is moving, it doesn't want to change its motion. It wants to keep moving. If an object is stationary, it doesn't want to change its motion. It wants to stay stationary. It's resistance to change. So this is related to its physical characteristics. It's related to specifically to the mass of the object you're talking about. And I talked about the shot put and the table tennis ball. They have completely different mass values and therefore they have completely different inertia values. The shot put having a big inertial value because it's a big mass. Table tennis ball having a small inertial value because it's a very small mass. So there are no actual units. We just talk about sort of the size of the resistance. We don't talk about specific numbers, or it doesn't have a unit, you know, it's not in kilograms, for example. In rugby, of course, you might have players that have a big mass and they would have a big inertial value. To get them moving, to change their motion or to slow them down, we need bigger forces than if we were trying to change the motion of this smaller rugby player. To stop him coming through would be easier than trying to stop this big player with a big mass with a big inertial value. So if you can connect inertia to mass, it really makes sense. So as I said, inertia is proportional to mass. The size of the inertia is directly linked to the mass, the size of the mass of the object. The greater the mass of the object, the greater its inertia. The smaller the mass, the smaller the inertia. That doesn't necessarily relate to size. So you could have something, you could have, for example, a golf ball, which is pretty much similar size to a table tennis ball. So the size is irrelevant, it's the mass that mattered. A golf ball is a higher mass than the table tennis ball, just to be clear. Okay, so again, other examples. To change motion, we've got to overcome the object's inertial value. So if I want to change the motion of this stationary ball, this ball is reluctant to change, it wants to stay stationary. In order to do that, I've got to apply a force that is bigger than this rugby ball's inertial value to move it. And so therefore I'm applying a kick force, an applied force, an external force, that's bigger than the value of this ball's inertial value, and it makes it move. If I didn't, it would stay stationary because it is reluctant to change. Similarly over here, as I was sort of mentioning earlier, if you've got an object, a rugby player with a very high mass, they have a very high inertial value. The force needed to change this object's motion, i.e. to slow him or stop him completely, needs to be bigger than the relative inertial value of this rugby player. He's got a big mass, therefore he's got a big inertial value, therefore the force needed to stop him is big, is huge. These players will struggle to stop him because of his inertial value. So importantly, you need to recognise that inertia and the reluctance to change motion relates to stationary objects and objects in motion. If you think about things like bobsleigh, so the bobsleigh is a heavy vehicle. The runners, the athletes have to go from being stationary, change this object's change this object's motion by pushing with a greater force as possible to overcome its stationary position to make it have high velocity at the start of that bobsleigh event. Sometimes we purposely increase the inertial value, and in this example, this sled has been given an extra high mass, so the weights have been added to it. So this object now has a bigger mass and therefore a bigger inertial value. For this athlete to change this object's motion from being stationary to running with it, it's harder for him. If they only had no weight, no sort of black weights on it, or less, it would have a lower mass, a lower inertial value, and you wouldn't need as much force to get going. Notably, going back to the bobsleigh example, the surface affects the inertial value. So actually the fact that this is on ice with low resistance factor and is on blades, which again reduces the resistance, makes overcoming inertia easier. If this had no blades and was laid flat on the grass, it would be harder for these athletes to change this object's motion. Similarly, from stationary to get it going is tough. You need a big force to overcome that inertial value. Once it's going, you don't actually need, it's almost easier once you've gained momentum. And we'll talk about momentum in a minute. Once you've got something moving, it's not so bad. I've just put this example in here just to try and give you applied sort of rationale behind things. Some sports have weight categories, age and or weight categories. So, you know, an event, the martial arts or weightlifting, a lot of contact sports are weight related or mass related, I should say. And that kind of makes sense. It might be unfair competition to have somebody with a big mass and a big inertial value. Remember, in some cases, the principles behind these kinds of sports might be to get your opponent, in judo, get your opponent to the ground. And if you have somebody with a huge mass, they have a bigger inertial value, and actually moving them or changing their motion, changing their position, is much harder than if you're matched evenly in a weight category or a mass category. So there could be some relevance to that. So, just to summarise, inertia is the tendency of a body to maintain its current state of motion, whether that's at rest or in motion, travelling in a straight line. The greater the mass, the more resistance there is to change. Whether it's a large mass, it's a big inertial value, small mass, small inertial value. If you want to slow down an object and it has a high mass and therefore high inertial value, that's harder. You've got to apply bigger forces to slow it down, and obviously the reverse is true. If you want to slow down an object which is low mass, has low inertial value, it's easier. You don't need to apply quite as much force. So inertia is all about resisting change in motion, whether stationary or whether it has a certain velocity and adds in motion. And the way we change motion is by having a net force, an unbalanced force, applying a force that is bigger than the inertial value. And just to be clear, I've talked already about balanced forces or unbalanced forces. I think I did in the Scrum example. So here we've got two teams in tug of war. You can see that the force their pulling force is both 300 newtons. That is a balanced force. There'll be no change in motion. Okay, so this team have an inertial value, a certain mass. If you add up all their masses, they have a certain inertial value. This team, add up their masses, they have a certain inertial value. Obviously, to win, one team has to pull more than the other team's inertial value. In this example down beneath, this team has generated a bigger force and has managed to move or to overcome their masses, their inertial value, and their muscular resistance, of course, as well. And this is an unbalanced force. There's more force being applied in that direction than there is opposing it. And we'll talk about balanced and unbalanced forces more. Okay, so moving on to the second topic then, we're going to talk about momentum. So in terms of which ball, daft question I know, but if you had to pick a ball that was thrown towards you, a bowling ball versus a tennis ball, I'm hoping you would all choose the tennis ball, and the reasons for it I'm sure you know, but you might not be able to articulate in terms of physics. Bowling ball obviously is a high mass object. It's very dense. It's, if it makes contact with you, it will harm you. Tennis ball, much lighter mass. Doesn't matter what size it is, it's about the mass of the object. So this bowling ball in motion coming towards you, we would describe it as having a high momentum. So if these two balls were thrown with the same velocity, i.e. they're travelling towards you at the same speed, we would still describe this bowling ball as having a bigger momentum than this tennis ball, because the difference is it has a much greater mass. And momentum is related to mass and velocity. So if these two objects were travelling at you at the same velocity, we can remove that from our equation, which leaves us mass being the same, being the key factor deciding the difference in momentum. The bigger mass of the bowling ball means this has a much bigger momentum, and therefore I obviously don't want this ball coming towards me. Another sort of question for you. Why is it that 100-metre sprinter needs to apply a larger force to accelerate, to build up speed at the start of an event? In the middle part of the event, they apply less force when they're running, and their speed is constant. And again, at the end, when they cross the line, they have to find large forces again to slow down. So it goes big force, less force in the middle, big force to, once you've finished across the line, to slow down. And you may have guessed, of course, that the answer is related to the momentum that that athlete possesses. Momentum is related to mass and velocity. So we need big forces here to accelerate, to gain velocity. Once we've got velocity, we don't need to apply further force. We are hopefully maintaining the same momentum. We've got high velocity. Our mass is constant anyway. We've already got high velocity. We don't need to generate quite as high forces to maintain that momentum. Momentum is almost carrying us along a bit. When we need to slow down after the finish line, we've got high momentum, and now we need to reduce it. Our mass is constant, so we need to reduce our velocity by applying forces in a sort of backward direction, and we often lean back a bit. When we need to apply forces to generate velocity forwards, this position is quite leant forward, isn't it? We're pushing backwards, so it pushes us forward. When we need to slow down at the end of a race, we'll lean back a bit, so the extra force that we're pushing on the ground pushes us back a bit and eventually slows us down, reduces our velocity, and therefore reduces our momentum. So momentum is to do with mass and velocity. As you can see this equation over here. Momentum, which is the letter P, equals mass times velocity. So momentum is defined as the quantity of motion that an object possesses, how much motion an object possesses. And we times mass by velocity. So if an object is still, not moving, we would describe it as having zero momentum, because mass times velocity, if it's still, is mass times zero, which is zero. If an object is moving at a certain velocity, it would be the object's mass times the velocity of the object gives us its quantity of motion. And it's a vector, so we need to determine which direction it's in as well. So momentum is inertia in motion. It's the reluctance to change its motion. How much momentum something has determines kind of how resistant it is to changing that motion. Slowing down once you're going can sometimes be harder. You know, if your car breaks down, you push it, it's hard to get it moving, but once it's moving, sometimes it's harder to stop it because it has this reluctance to change once the momentum gets going. So momentum is a vector. Because velocity is a vector, we have to therefore have a directional factor. We should have a directional factor in it. Mass in most objects doesn't tend to change. It's the velocity that can change, and therefore it's the velocity component that will affect an object's momentum. If you roll a ball along the ground, once it leaves your hand, it probably has high velocity and will have therefore higher momentum. The longer it rolls on the ground, probably it will begin to reduce its velocity because friction will slow it down, and therefore its momentum will be reduced as it travels further. That's kind of logical. So just to reiterate, momentum is this equation, mass times velocity. There's a sort of triangular version of it. I quite like this example on the right here because it shows the two components. If you've got a bowling ball which weighs 7 kilograms but is only travelling at 1 meter per second really slowly, so we would do mass times velocity. 7 times 1 is 7 kilograms per meters per second. Okay, so it has a momentum of 7 kilograms per meters per second. If we took this tennis ball, which only weighs 0.07 of a kilogram, and we times it by its velocity, now you can clearly see it's travelling significantly faster at 100 meters per second. So if we do mass times velocity, we do 0.07 times 100, we also get 7 kilograms per meters per second. So the mass is bigger, but the velocity is slow. The mass is smaller, but the velocity is higher. And these two objects would be, in this context, travelling with the same momentum or possess the same momentum value. Okay, so here's a few examples that I want you to have a go at. You've got a rugby prop. Their mass is 90 kilograms. They're travelling at 10 meters per second, which is perhaps quite unlikely. You need to calculate their momentum, and the equations up here. So pause the video, have a little go at that. Here's another example, a long jumper on the run-up, travelling at 9.67 meters per second, and their mass is 65 kilograms. Another example, so we've got a team of athletes whose collective mass is 630 kilograms. There is a limit to the bobsleigh, I think, weight as well. Now, for a bobsleigh team, it's quite an advantage having a high mass, because once they get going, the momentum that they generate travelling down the the ice route or path track is advantageous. So they're travelling at a velocity of 42.5 meters per second. You calculate their collective momentum. So we talked earlier in the video about different momentums, or an athlete possessing different momentum values in different stages of the event. So calculate the momentum of the athlete in the starting blocks and calculate the momentum of the athlete in the middle of the 100-meter race. Okay, I think this is one of the last tasks for you. So rugby team momentum, we've got 3 different players, different masses. So calculate the momentum of each of them. They are travelling at different velocities. So mass times velocity, mass times velocity, mass times velocity. Calculate their momentum and then answer these questions. Which player has the greatest inertia? Why do you think that? Which player would you least like to tackle and why, given they're all in motion? And how much mass would player 2 have to gain to have a higher peak momentum than player 3. So lastly, I just want to try and show you how actually in some other sporting actions we use momentum to assist us. This power clean technique, you may be familiar with it anyway. The video, I'm sure, will go into it, but hopefully it will play for you. But basically, once the athlete can manage to overcome inertia, you imagine this barbell with these weights on has a very big inertial value. That this athlete has to generate force to overcome, i.e. to lift it. But once it does gain motion, once it does gain some upward velocity, vertical velocity, in this positive direction upward, it has momentum, it has a value of momentum. Right here, still, before they do their lift, the momentum value is 0. It's mass times velocity. It's not moving, 0. Once it can generate some upward velocity, we've then got mass times that velocity. That momentum is really helpful. And this object doesn't want to change its motion. It will, of course, so it will carry on travelling upwards until an external force changes its motion. Just have a think for a minute. What force, what would be affecting the motion of this upward movement? What will ultimately make this barbell stop moving upward? See if you can think through that yourself. Hopefully you come up with gravity. Gravity will be acting downwards against it. But in that phase where the upward velocity is decent, for want of a better word, where the upward direction movement has some momentum, you can see the athlete will quickly squat to get their body position underneath the bar, and therefore they can then use their muscular force in their legs to complete the technique. It's just going through the technical points which we don't necessarily need. So you can see this is now their legs have gained upward velocity, and while there is upward momentum, the athlete dips underneath the bar and gets into that stable position where hopefully their legs are strong enough to then support the bar itself. Okay, so that completes the content of inertia and momentum. Obviously, in terms of your assessment, giving a variety of your own sporting examples, you need to recognise, obviously, what inertia is, how it can differ between different objects. Please remember to give examples that are equipment objects as well as human example objects, if you like. Make sure you relate to the fact that inertial values of objects differ depending on their mass. So inertia is related to their mass. Inertia is a scalar, momentum is a vector. Momentum is then a description of the motion that an object possesses. And again, it's highly related to mass and velocity. The fact that mass tends to be constant means it's the velocity of an object that often is key to changing an object's momentum. Talk about changing momentum from being stationary to a moving object, to the forces required to move an object, to the forces required to slow an object down or stop it if it is in motion, and the forces required to stop an object with a higher momentum, a higher velocity, or a higher mass, obviously will need to be much higher. So there's lots of sports applications you can have here. Okay, so as always, you can message me if you have questions, but this should hopefully explain what you need. You've got the textbook chapters available to you. There's lots of videos online that help you with these concepts as well.